data and analytics won't be a competitive advantage for long, it's going to be a necessity, it's still not entirely clear how, as a full company, we're going to get to a place from where we are now to where we need to be, where decisions are driven by insights, right? And correctly driven by insights. Because it turns out, the problems I discussed earlier, similar things happen, and we have similar cognitive gaps when we're looking at numbers that appear to be simple. We think we can expand on them and come to some other conclusion to drive strategy, but that is rarely the case. In order to get to the point where we can be a company that really focuses on analytics, we have to go back to our core values. So the two that come to mind are thriving together and rethinking routine. Pioneering simplicity is also important, but how does that come into factor here? Well, one, we already have an established routine for how decisions are made throughout all levels of business. And it's really hard to get people and motivate them away from their routine, right? How they take something that is provided to them and use that to make a decision. And analytics is so hard that it's not something that an individual or an individual team could do. It requires too much specialization, especially with the kind of data that we're dealing with, that the only way to be effective is if we all work together to come up with a solution. Now, I know I said that this wasn't going to be a math-heavy talk, even though it's mathematical paradoxes. I don't expect the people in this room to know a lot about probability and statistics. So as a background, let's take a look at two basketball teams from this state. The way you would interpret this is if you go to the bottom left, you look at free throw percentage, and U of L has 70%. That means it's 7 out of 10 times that they've taken a shot, they made the basket. If you look next to it, you'll see that Kentucky has 80%, meaning they make 8 out of their 10 shots. That's higher than U of L. That's the correct way to interpret it. If you then look up and you see the 3-point percentage and 2-point percentage for University of Kentucky, you'll see they're also higher than U of L's shooting percentages in 3-point and 2-point respectively. I made up these numbers, so you guys probably know what team I prefer, right? And it's also probably pretty obvious what the highest overall percentage would be, right? It's University of Louisville. So now you know what my real favorite team is. It is University of Louisville, the Cardinals. And the reason that something like this can happen, even though intuitively we normally don't realize that it's the case, is subconsciously we're thinking that they're taking the same amount of shots at the 2-point line, the 3-point, the free throw line. But that's not necessarily the case. If you know your team sucks at shooting 3-point shots, maybe you shoot more from the 2-point or inside, right? You drive in and you try to make a basket. Maybe that makes you more likely to go to the free throw. So even though you're shooting those not as well as the other team, if you're doing them more often than the other team, your overall average goes up. This is what's known as the Simpsons paradox. And this is a very common problem that business partners face at Humana. Let me give you an example why. So I work in pharmacy analytics, and I like to think of things from that perspective. Imagine we receive a request from a business partner to evaluate which 2 drugs are better. This injectable that's very expensive or a generic drug that came to market recently and is substantially cheaper. We may want to move members away from this expensive injectable to a generic drug if it's as effective as the more expensive one. So we receive somewhat of a non-specific request. Which drug is better? And we're given some information about, this drug treats these conditions, and this is what we consider a positive outcome would be. We do the analysis, it's relatively straightforward, and we find that drug A is better, 85%. So if we stopped here, that would be the end of the analysis. The injectable is better than the generic drug, and we should be pushing our members to the generic drug. But say you take a step further and you decide to look into the data a little bit more, and you realize that these 2 drugs are used to treat 3 disease states, and you want to see how effective they are on any of the given disease states. You do this analysis, and all of a sudden, the generic's better. Not only is it, the overall rate is the same, right? But it's better in disease state 1, it's better in disease state 2, it's better in disease state 3. So no matter what disease you have, you'd be better off with a generic. How on earth is it possible for us to come to two different conclusions based off of what seemed like a simple question? Which drug is more effective? And I know a lot of you are questioning this right now, but you can Wikipedia it later. The Simpsons paradox is a very common problem that people have. And not only this, say we decide we don't want to look at it from a disease state matter, we want to look at it from demographic data, right? How do women compare to men? How do different age groups perform? And oh look, the analysis just swung the other way. So now we have three different answers essentially to what is supposedly a simple question: which drug is more effective? How do you answer this? Well, the only way to answer this appropriately is to understand the goals and strategies the business partners that we work with have in mind. And without that context, there's no way to possibly answer this question correctly. This is supposed to be a simple question. And our business partners expect a simple answer because they don't have time to dig through the data and interpret it. The only way we get from where we are today to where we're going to be tomorrow is by rethinking routine and working together.
Isn't that because the percentages are misleading on how many universe? I mean, if you just use that drug one time, it's effective at 100%, right?
Exactly, right? So the intuition is that these groups would all be weighted equally, but that's rarely the case. So in the case of a generic, it's entirely possible that different types of members are being treated by there in the different disease states, or you have different numbers in any of the subgroups. So weighted average is an important distinction. But at the end of the day, that's where the problem lies, right? Your full number is not a weighted average, it's the whole number. But when you look at the individual breakouts of the categories, then you have a different result. Because it is true, this isn't like a trick of math. It really can be the case that you'd be better off in any disease state taking the generic drug, but this overall number appears to be better if you look at the whole population and you don't control for differences in those populations. Oh, and there's another clarifying thing. These could be the same number of people in the population, right? It's not just that there's more people in one than the other. It's that the subgroups in them would have different numbers. Okay, on to the next problem. All right. This is actually one of my favorites. So for this, we're going to be talking about birthdays and the likelihood that two people are born on the same day. When we say that, we're going to talk about month and day, not take year into account. So in this instance, these two individuals born on January 22nd, we'll say that they're born on the same day. Similarly, we're going to make a simplifying assumption and say you have an equal chance probability of being born on any given day of the year. So the member born August 10th, same likelihood of being born August 10th as February 14th. There's no difference. It's not true in census data, but it's true enough for this. Since there are 365 days in a year, you have a 1 in 365 chance of being born on any given day of the year. So if I say, what are the chances that my boss is born on the same day as me? Well, I'm born on a specific day. So the chances of him being born on that day, the odds are 1 in 365. Now I'm going to pose the question to you, how many people need to be in this room for the chance that two of those people have the same birthday? Right? Any two people in the room. And to help you out with the math and the intuition in your head, let me give you some numbers. 1 over 365 is equal to roughly 0.25%, and 183 over 365 is roughly equal to 50%. So in order to guarantee in order to allow for the possibility you've actually covered half of the birthdays in the year, you would need to have at least 183 members. But remember, that can be a little bit misleading when you're trying to decide. So I want everybody to get a guess in your head. Is this number, is the answer going to be a lot more than 183? Is it going to be a lot less than 183? For those of you who have heard of this problem before, you already know the answer. For everybody else, prepare to get your mind blown. The answer is 23 people. There are 365 days in the year. But if you put 23 people in the room, there's a better than 50% chance two of those people share the same birthday. This is what's known as the birthday paradox. It's a problem that arises from multiple ways, right? One, a lot of people don't have a really strong intuitive grasp of probability, which is strange because generally there are two groups of people. Those who think probability is easy, those who think probability is really hard. They're both wrong. Probability is super hard. Okay, it gets really complicated. But how this might apply to a request that we receive at Humana and Pharmacy Analytics is when they're asking for the likelihood of an event occurring, and we provide them a number like 1 in 365, and then they take that number and think, this is really rare. We don't have to worry about something like this happening in our population. Or if it does happen, it won't happen very frequently, right? It's a very unlikely situation to occur. But the truth of the matter is, it could be very common. So it's very important that you don't take data that's provided to you and try to make that next intellectual leap, right? To derive more from it than what was provided unless you're really sure you understand thoroughly what that number represents, and two, what that number can be used for. All right. The next thing we're going to be talking about is also a very well-known problem. It's not a paradox per se, but it's also pretty unintuitive. It all starts with an old game show where a contestant would come on and pick from one of 3 doors. Behind 2 of the doors there are goats. Behind one of them there's a car. If you get the goat, that basically means you lose, huh? Unless, I guess some countries they really value goats. You want the car. So let's work through this and say you pick this far door on the right. You don't know what's behind it. It could be a goat, it could be a car. Since you don't know, there's a 1/3 chance because there's only one car and we have 3 doors to choose from. Now, here's where it gets interesting. The host of the show is going to go and open one of the remaining doors. Not one that you picked, and not one that has a car behind it. The reason he's going to do this is he's going to pose a question to you. He's going to say, okay, this door has a goat behind it. Do you really want to keep the door you have, or do you want to pick the other door, since there are 2 doors remaining? The question is there a smart strategy you should take? Should you keep your door? Should you switch doors? Or is it 50-50 and it doesn't really matter? Now, there are only 2 doors remaining. That is a fact. One has a car and one has a goat behind it. You don't know which one. So if at this moment you were just to pick, if somebody else who didn't know any of this was going on came out and picked, it would be fair to say that there was a 1/2 chance. Either way. So you can flip a coin which door you want. But that is not the setup of this problem. And if you think right now that there's a 50-50 chance and it doesn't matter what strategy you take, you're wrong. The reality of the situation is that switching doubles your chance of getting that car. There's a 2/3 chance that you're going to get the car if you switch. While if you stick with your door, there's only a 1/3 chance. This insight is so unintuitive that when it was first written about in a paper, mathematicians from all over the country supposedly wrote into the author, or to the paper, I think, that published it, complaining about it, saying that it was not at all accurate. One of my math professors, and he's no slouch, he was a PhD from Georgia Tech, doing research in combinatorics, so basically things like probability. When he first heard about this as an undergrad, he didn't believe it so strongly. He thought this was just a trick of math, that he wrote a computer program to test it out. The program would randomly pick a door, one of the other doors would be open or be the wrong door, and then you would switch. And guess what? 2/3. So even as unintuitive as this is, even as much as we don't want to believe this to be true, this is true. This isn't a trick of math. It's what's known as the money hall problem, if you guys want to look it up and learn more. So again, this is just to reiterate just how hard problems in probability can be and how unintuitive they can be. So when we see some numbers provided to us, we have to be very careful about the setup of the problem. And the only way you can be careful about the setup of the problem is if, as an analyst, you understand the business decision that is trying to be made. And the only way for the person trying to make a business decision to ask the right question is if they understand enough about analytics to formulate the question in an appropriate way. All right. And here's the last problem I'm going to discuss. The first three, they're all real things. They are things that people make incorrect, intuitive leaps about all the time and come to the wrong business decision as a result. This next one's just more for fun. So this is a slightly different take on the typical problem, but imagine Zeus and Hades are having a contest, right? They want to see who can fill the most balls in the urn. The balls are all numbered, 1 through infinity. And each time they put in a ball, or put in 10 balls, at each instance they put in 10 balls, they're going to take 1 ball out. Why they're doing this, I don't know. The gods are weird. So they're going to do this increasingly fast. The first time they put in balls, they're going to do it at 11:30, then 11:45, then 11:52, so on and so forth. Always half the time between whatever time it is now and the remaining time before the clock strikes midnight. The ball they take out, though, is where the strategy diverges. Hades is going to increment up, right? He's going to take out ball 1, and then the next time he's going to take out ball 2, and then 3. But Zeus has a different plan in mind. He's going to take out factors of 10. So he's going to take out ball 10, and the next time ball 20. And so take a look at this, see? So next time they put in balls 11 through 20. Hades is taking out ball 2. Zeus is taking out ball 20. And they're just going to continue in this pattern. But it's the same thing each time. They each put in 10 balls. They each take out 1 ball. So I guess if you want to think about it in one way, it's a net 9 balls, although that's not the way the problem's formulated, so be careful in thinking. At midnight, who won the competition? Who has more balls? Or is it a tie? I mean, obviously it's a tie, right? It is not a tie. In fact, there couldn't be a greater difference in the number of balls between these. Hades has 0 balls in his urn at midnight, while Zeus has an infinite number of balls in his urn at midnight. This is what's known as the Ross-Littlewood paradox, because you would suspect that since you're putting in 10 balls and you're taking out 1, they're both doing the same thing, but they're just changing which ball they're taking out. But that shouldn't matter. And it doesn't, depending on how you formulate the question. So if I was saying that they were putting in a net 9 balls, and that's the way the problem was formulated, well then they would both have an infinite number of balls. But you see, the problem is, tell me a ball. They're all numbered, right? So tell me a ball you think is in this urn, and I'll tell you a time when Hades took it out. But no matter how long we wait, ball 1 will always be in that urn, in Zeus's urn. So order matters. In high math, order matters. And this is one of those more fun paradoxes. Of course, this isn't something that could happen in the real world. This is known as a super task, and these things don't occur. But we do use this kind of math all the time. Have you heard of calculus? So when you're taking an integral, you're basically doing something like this. When you're taking a derivative, you're basically doing something like this. All right. So I don't want to blow anybody's minds anymore. We talked about it a lot today. And I'm sure most of you are questioning some of the things I put on the slides, and I fully encourage you to investigate them further on your own. The results are unintuitive. If you haven't heard them before and you weren't shocked, well then I'm shocked. Because the first time I heard each and every one of these, I couldn't believe it. And the first one, the sphere one, is the Navier-Tarski paradox, in case you're interested in looking at that. The counting number 1 isn't a paradox, it was just a very weird quality that I shared with it. So to wrap up, analytics is hard. Probability is hard for a lot of different reasons. And I think the only way to move forward is to really, to some degree, remove our ego from the equation. That we think we know how to interpret data. So if you're looking at data and within like 30 seconds, you know the right way to interpret it, well, either you're a really big genius, like once in 20, 30 years come along kind of genius, or you're at a pretty substantial risk for misinterpreting what was provided to you. There's a lot of movement in the space to make things visually appealing, right? So that's kind of a tangent. Get a graph, and people are like, oh, remove this, and let's make it, flat and very attractive looking. And that's great. And it tells a story. You want to get all this distracting information away. And that's perfectly fine as long as you can somehow ensure your audience doesn't take that information and extrapolate. Because they probably can't. Regardless of what it is, they probably cannot extrapolate. And you're always going to face that risk that they're going to try to take it and somehow infer more from it than what is really being shown. But when you do that, you might be hitting one of these paradoxes. Okay, thank you for your time. If anybody has any questions, don't make them too hard because I am not a math major. So. Great, and thank you.